Hey everybody, it's Bradley Bush again with another algebra video for you. Today we're talking about oblique asymptotes. They're also called slant asymptotes, and I'll refer to them as slant asymptotes most often. The to-do list today, first we'll review rational functions quickly because that's where you find slant asymptotes. Then we will talk about the definition of a slant asymptote. Then we will discuss how to find them if you're given a problem, and then we'll actually do a work problem. I'll also put the timestamps for these in the video description in case you want to skip ahead. All right, rational functions. Here's the quick version. A rational function is fairly simple. It is just a function that is a polynomial fraction, meaning it has a polynomial on the top and it has a polynomial on the bottom. So it's a fraction. It's a fraction that has two polynomials, one on the top, one on the bottom. And the domain is everything except, meaning all real numbers, except the x values that make the polynomial in the bottom equal to 0. So you kick those out. Vocabulary that is helpful is asymptote. I don't know, it's kind of a weird word, right? Asymptote. It's got a whole bunch of syllables that you wouldn't think would go right next to each other in a word. An asymptote is kind of like, this is the layman's version here, it's kind of like an invisible line that gets closer and closer to the graph of a curve without touching it, as either the x-coordinate of the graph goes to positive or negative infinity, or the y value, the y-coordinate of the graph, goes to positive or negative infinity. And we'll give you some pictures so that you can see what exactly I'm talking about. There are three types of asymptotes: horizontal, vertical, and of course the oblique, the slant asymptotes. Two very common rational functions. One is 1 over x, and the other one is 1 over x squared. Here is a graph of both of those and some interesting information below. If you want to see or listen to me discuss all of the information here in detail, please check out my Intro to Rational Functions video. But the quick version, I should say before I move on, the 1 over x has a bow and arrow shaped curve, kind of like an L shaped curve in the top right, and then one in the bottom left. And they kind of look like they're both shooting arrows towards the origin. And the 1 over x squared function has a very similar bow and arrow shaped function or curve in the top right, but the one that was in the bottom left is now popped up into the top left. So it kind of looks like the Atari symbol if you are into old school gaming. All right, some examples of other rational functions, just some curves that you might see. You can get some really interesting curves out there. Some really interesting graphs from rational functions. So you can get totally N-shaped curves, you can get L-shaped curves, you can get elongated S-shaped curves, you can get curves that kind of look like a boomerang. Two boomerangs, in fact. So you can get a lot of weird stuff. Let's talk about arrow notation. So this comes up a lot in asymptotes and in their definitions. So if you ever see x and then a right arrow and then something like an A with a positive in the power, so a plus sign in the power, so A raised to the plus sign, that x right arrow, A raised to the plus sign, means x approaches A. A is some value on the x-axis, like 5. X approaches A from the right, so you're starting from above. So say if A is 5, then maybe you go 7, 6.5, 6, 5.5, and you're approaching 5 from the right side of the number line. So if I drew a graph here, this is my x, say this is A equals 5, and of course that is also the x value. It's a pretty terrible 5, isn't it? If this is A, and then say maybe here's A's 5, so this would be 6, 7, 8. So if I'm approaching A on the x-axis from the right, that means I'm coming from a higher or bigger number, and I'm moving towards 5, which is A. So the concept isn't really crazy or new. It's just the symbols that they're using to represent the concept might be new to you. And x, and then a right arrow, and then a raised to the negative power. So there's a negative, a minus sign in the exponent of a. That means x approaches a from the left. So we are actually coming towards that same value a, but from the left side, so from smaller values to bigger. We can also not just approach a specific value on the x-axis. We can say let a get as big as we want, and it keeps going on forever, infinitely. That is represented by x and then a right arrow and then infinity. So x, right arrow, infinity, that means x approaches infinity or increases without bound. X, right arrow, negative infinity, that means x approaches negative infinity or decreases without bound. How do I find a slant asymptote? Well, if my rational function has a polynomial at the top and the polynomial at the bottom, if I looked at the polynomial at the top and I looked at the biggest exponent, say that's called the degree mathematically, the degree of the numerator is the highest power in the numerator, say that is n, and say my highest power in the bottom or the denominator was m. So the degree of the numerator is n and the degree of the denominator is m. So say n, which is the exponent at the top, is bigger by 1. So maybe the one at the top is 3 and the one at the bottom is 2. So the exponent at the top, the biggest exponent at the top is bigger than the biggest exponent at the bottom by 1. If that occurs, then you can have a slant asymptote. And the way you find it is you actually perform the division that's represented by a rational function. So you take the polynomial at the top and you divide it by the polynomial at the bottom by long division or synthetic division. And then once you finish the division, you throw away the remainder if there is one, and you keep the rest, and that you set equal to y, and that's your slant asymptote. It's actually pretty simple. Let's do an example. So if we want to find the slant asymptote of the following function, and the function we're given is x squared minus 4x minus 5 in the top, and in the bottom, x minus 3. Over to the right, you see a picture of this, and you see the slant asymptote. It's a slanting towards it's going up as you move right on a slant, and you have a curve that has one part of the curve that's above the asymptote and one part that's below. The part that's above, as it goes down to the left, kind of meets the slant, and it goes to the right, it kind of veers off and goes straight up. And the part that's below goes straight down, the same place the one above goes straight up. And then as it goes up towards, it's coming down from beneath and going up towards that slant asymptote. And as it gets closer, it veers off to the right and keeps following it, but never touches. So it kind of looks like an H a little bit. All right, let's find this slant asymptote. So if we want to do a division, we could do long division, but I'm not particularly excited about doing long division. I'd rather do synthetic division. And this is perfect. This case is perfect for it because in the bottom we have x minus 3 in our function, and that's perfect for the setup. So x minus 3 is actually the factor we use. In long division, we use this factor x minus 3, but in synthetic division, we set that equal to 0 and solve for x, and that gives us just 3. In synthetic division, we just use the 3 instead of the x minus 3. So we plug the 3 in its spot. We take the coefficients of the numerator, which are 1, -4, and 5, and plug them in a horizontal row. And below that horizontal row, there's kind of a blank line, which we'll fill in with numbers, and then a solid horizontal line, and then another blank row, and we'll fill that in with numbers. So what happens is this 1, the first of the 3 numbers that came from the coefficients, 1 we drop straight down. So at first that comes down, and we have a 1 at the bottom. Then we multiply the 3 out front by that 1, and we get 3. We add the 3 we place just below the -4 to the right of the 1, and then we add the -4 and the 3. -4 and 3 give us -1, and then we multiply the 3 out front again by -1, and we get -3, and then we put that in the spot to the right. So each time we're putting another spot, we're putting the number we get to the right of the previous one. And then that -3 is directly below the -5, and -5 and -3 give us -8. It's not a very good arrow I just drew right there. I'm going to fix that. There we go. So this -8 is our remainder. Remember, we're going to throw the remainder out. So you're wondering, well, that's great. Now what do we do? Well, if you remember from the beginning, we started with x squared, and we had an x column, then we had a constant column. Once we go through one step of division, we lose an exponent. So now this is the x column, this is the constant, and this is the remainder column. So our answer to the long division problem, x squared minus 4x minus 5 divided by quantity x minus 3, that is x minus 1, and then we have a plus, we have a -8 over x minus 3. So the coefficients, the x and the -1, just came from the 1 and -1 in the bottom from our long division. So now we've finished our synthetic division. We locate the remainder and we get rid of it. And what's left? That is our new slant asymptote. So our slant asymptote is y equals x minus 1. And that is what you see in the graph, the black dashed line. So that's it. It's not too terrible. Hopefully this was helpful. If it was, subscribe to the channel, give me a like, and thanks for watching.